Hello all, welcome to Intuitive Stats. So this video is on something called linear regression. Linear regression is all about fitting a line to a set of data points. Now the term regression was first used by Sir Francis Galton. However, the mathematical framework behind regression was the contribution of Sir Karl Pearson, whom we already know by Pearson's coefficient and several other works in statistics. Linear regression is not the only type of regression that we know, because there are other versions like logistic regression, if you are aware of, and several other versions too, which were primarily developed by Sir Ronald Aylmer Fisher. So this was a little bit history of regression in general, but now let's look at this example to understand the idea behind linear regression. So this is a plot on average weight and age of children, which means that when age is 1 year, the corresponding weight is seen to be around 3.3 kgs. And similarly, when children get 6 years old, the weight seen is around 13 kgs. So as I mentioned, linear regression looks to fit a line to a set of given data points. So let's fit a line to this data. But now the question is, we can fit many lines to this data set. But which line or which particular line would be fitting the best to this data? Or in other words, which is the line of best fit? That is what we intend to find. So to determine the line of best fit, we need to perform some algebra. And let's jump to the mathematics of fitting a line to this data. So let's assume that this is the line which is the best fit to the data. Let's just assume that. Now we know that x here represents age and y here represents weight. So if this line fits the data in the best way possible, the error term, that means the difference between the predicted value, which should lie on the line, and the actual value of y, that means dependent variable, it should be minimum. Error here is represented by lowercase alphabets, and I would appreciate the fact that the error which we are trying to minimize here is not the one at a time error, but it is all the errors should be minimum possible at the same time. So what we are exactly looking for is to minimize the sum of errors. But there is a problem here, because A, E and F, the errors here will be negative, or it would be opposite in sign compared to B, C and D, because they lie on the opposite side of the line. So how to deal with this? Because if we keep this as it is, what will happen is these three terms and these three terms will get cancelled, or maybe there is a chance that subtraction takes place. Okay, but this won't fill our purpose. So maybe another school of thought is to try minimize the square of sum of square of errors, which is this. So our objective here is to minimize the sum of square of error terms. Now, generalizing this, we know that error is the difference between the observed value, which is this one, yi, and the predicted value, which is this one, y predicted. So for ith term, or for any term, because we are generalizing this for any set of data points xi, yi, error for any ith term will be given by yi, which is this one, and the difference between the predicted value, which is mxi plus c. Now squaring this error term, we get this thing. Again, we told that we wanted to minimize the sum of square of errors. So summing the errors for n data points. So this was for one data point, this is for n data points. So this is the sum of square of error terms, and this is what we aim to minimize. Now in calculus, we are already aware that if we are in search of minimizing something, we need to differentiate it with respect to the variables which we intend to find, here m and c, or the variables which vary. And here the reason why we differentiate it with respect to m and c is because m and c are parameters here. In the language of statistics, we use the word parameters. And why we use parameters, I'll explain it with an example. Let's say y equals 2x plus 3 is a line. And please appreciate that this is a line, not a family of lines. So this is by y equals 2x plus 3, I am specifying a particular line, and where m is 2 and c is 3, y equals 2x plus 3. So if we specify m and c, we'll know which line it is. So exactly what we are finding here is m and c. So differentiating it with respect to m and c, we get these two terms. Now, I would also like to state that summation and differentiation are separable. So still, if you are interested in going through a short proof on why summation and differentiation can be separated, please check out the link of the video in the description given below. So that might help you a little bit. So getting on to the next page, if we apply the summation operator, we get this. Now if you observe this is a system of linear equations in two variables, m and c. And let's look quickly at an example just to get the gist of what we've developed here. So this and this, x and yi, is the set of data points to which we intend to fit a line. If we intend to fit a line to this data point, we'll need to plug in the values of these terms, summation xi square, summation xi yi, and we'll be getting two equations in terms of m and c. So plugging the value of summation xi yi, that is 327.8, and so on, summation xi square, which is 140, you'll be getting these two equations. And solving this, we'll be getting values of m and c, and putting the m and c in y equals mx plus c, which was our assumed line of best fit. This is the line which is a best fit for this data. Now this is a plot of this line. So there is nothing much here, but the term r squared appears here because no matter what or how the data is, you'll always be able to find a line of best fit. But whether or not you should depend on that line for prediction, that is the question. So that question is answered by r squared. Now r squared here 80.8987 tells you that the line explains around 89 or 90% of the variation in the data. So this is a very good capture of pattern, and we can rely on this line for predicting further values. Let's say if we wanted to find out what is the weight when the age is 8 years, so the results will be very close. On the other hand, if the value of R squared was 0.2 or 0.3, that line was absolutely not a good one to be dependent on for predictions. So this is it for linear regression. Please comment, like, share, and please do subscribe. And also, I would appreciate if you could tell me what videos in mathematics or statistics would you like me to make. So till then, goodbye. This is Ronak Tiwari signing off from Intuitive Stats.